Question 1a, prove that root 5 is an irrational number. So I'm not going to prove about existence, we're just going to prove, we're going to assume it exists. So let's suppose for contradiction that root 5 is rational. As such, there exists a p over q belonging to the set of rational numbers such that root 5 is equal to p over q. We may assume, without loss of generality, that root 5, p over q rather, is in its lowest form. In other words, we've divided out all the common fractions, the common multiples, and this is now in its lowest form. Square in then gives 5, square that side, square this side, p over q squared is equal to p squared over q squared, and that implies that p squared is equal to 5q squared. Move the q squared up to be with the 5. So p squared has 5 as a multiple. But this implies that p has 5 as a multiple. And I'll put a little footnote because that needs to be proved, that assertion. So there's a footnote there. So, but this implies that p has 5 as a multiple. As such, p will equal 5r for some integer r belonging to the set of integers. Consequently, we see that so let's substitute then. P squared is 5r, so put that in there. So 5r squared equals 5q squared, and 5r squared will be 25r squared, won't it? Divide by 5 both sides, and that tells us, reading from right to left, that q squared is 5r squared. Here, q squared also has 5 as a multiple. As such, or this implies, q has 5 as a multiple. And that's again the same invocation of the proved property that when a square number has 5 as a multiple, then the number itself has 5 as a multiple. And we need to prove that in the footnote. So, this is a contradiction, but this is a contradiction. Since both p and q have 5 as a factor, and we presupposed all the common factors had been divided out. So we can conclude then, so our initial assumption is wrong. namely that root 5 is rational. So our initial assumption is wrong. Consequently, root 5 is not rational. In other words, it's irrational. So we just need to prove that little footnote. So let's put it here, and the property. So let's move down and turn our attention to this now. Let's call it use a symbol. U belongs to Z. So for any integer Z, if U squared has 5 as a factor, this would then imply that U has 5 as a factor. So we need to prove this little footnote proof, don't we? So let's have a look at this then. So, if U does not have 5 as a factor, then there will exist an integer s such that U will equal 5 lots of s plus 1, or 5s plus 2, or U equals 5s plus 3, or U equals 5s plus 4. That's about it, because it doesn't have 5 as a factor, so it can either have, when you divide by 5, the number U, you'll have it going into an integer with remainder 1, 2, 3, or 4. No other cases pertain, do they? So here in this case then, U squared, if you square this bracket you get 25s squared plus 10s plus 1. U squared equals 25s squared. 10 and 10 are 20, plus 4. 25s squared, 15 and 15 are 30, plus 9. And U squared equals 25s squared. 20 and 20 are 40, plus 16. So here we observe, or we see, that U squared also does not have 5 as a factor in each case. Because if you divide this by 5 you get remainder 1. Divide this by 5 you get remainder 4. This by 5, this goes in, but it will leave remainder 4. And this one will leave remainder 1, won't it, at the end. So we can observe that when we look at it case by case, all 4 cases. So here we see that U squared does not have 5 as a factor in each case, but U squared does have 5 as a factor. But U squared does have 5 as a factor. So the only conclusion we can draw from this then is that so U must have 5 as a factor. And the proof is complete.